All right. Chapter 34, part 2. We're going to start off 34.5, which is Ohm's Law. Now, I'm going to put out a video probably sometime next week that goes over some of the math from chapters 34 and 35. Ohm's Law is going to appear in this video, but I'm going to try and, describe the equations and things like that. I don't think the book does a great job as best I can. But Ohm's law basically states that current in a circuit is directly proportional to the voltage impressed across the circuit and inversely proportional to the resistance of the circuit. What this boils down to is current we refer to as I, voltage we refer to as V, and resistance we refer to as R. So I, current, is equal to V voltage divided by R resistance. I personally prefer a mathematical algebraic readjustment of this law to V equals IR, voltage equals current times resistance, but that's me. He has always liked to do this, thing with directly proportional, inversely proportional, which is fine. But again, the direct proportion just tells us that voltage is on top, and the inverse proportion of the resistance tells us that it has to go on the bottom when comparing it to the current. So again, current equals voltage divided by resistance, or I equals V divided by R. So electric resistance we measure in a unit called the ohm. It was named after George Simon Ohm, who was a German physicist who tested wires back in the 1860s, somewhere in there. And basically, he just wanted to see what effect the resistance on a wire, different types of wires, had on the current that flowed through a circuit. He made everything the same length of wire, same diameter of wire, all that kind of stuff. But he was using, gold wire and copper wire and silver wire and tungsten wire and all kinds of different wires to see what would happen. And what boiled out is something that became known as Ohm's law, that current is equal to voltage divided by resistance. Now, the symbol that we use to show resistance is the Greek letter capital omega. Kind of looks like a two backwards and a two forwards meeting each other. But this is it over here that the mouse is talking about. But anyway, for a given circuit of constant resistance, current and voltage are proportional. And so voltage goes up, current has to go up. Voltage goes down, current has to go down, and so forth. So if twice the current flows through a circuit, we're going to have twice the voltage to make it happen. And so the resistance, though, has that inverse relationship. And so with the resistance, if we double it in a circuit, what we're going to see is that the current would be reduced or cut in two or halved. And so the relationship among the units of measurement here is that 1 amp is equivalent to 1 volt divided by 1 ohm. And so I take 1 volt, push it across a circuit that has a resistance of 1 ohm, we're going to get a current of 1 amp. If we take the voltage and bump it up to 12 volts, keep the resistance the same, then what we will see is 12 divided by 1, or 12 amperes in that particular circuit. Again, I don't prefer I equals VR that the mouse is talking about over here. I prefer V equals IR. Just a personal preference, but just remember it one way or the other. Again, get it on your formula sheet for your 34-35 quiz and your electricity and magnetism test coming up in a couple of weeks. So the resistance of a typical lamp cord is much less than 1 ohm. A typical light bulb, the resistance might be 100 ohms. This is why the light bulb glows with a higher resistance. It's going to slow those electrons up, and it generates heat. And once that heat is generated, it is going to glow white hot, and that's why a light bulb glows a white color. In a iron or an electric toaster, you might have a resistance of 15 to 20 ohms, which is going to provide the heat that heats up that iron or heats up that toaster and toasts your toast in the morning. Now, you may have run across resistors before, maybe not realize what you were looking at, but these resistors we can see here all have different color patterns on them. Each one of these color patterns, you can go to a book. I would never be able to tell you what these were without going to the book. This one is a silver, red, red, red. Well, a silver, red, 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 for instance, might be a 10 ohm resistance, but this is a silver, red, red, gray. Silver, red, red, gray might be a 5 ohm resistor. I don't know hide nor hair from which one it is without looking in a book, but you can see each one of these color codes tells us the different resistances that these particular resistors have. And you would see these in your TV and your radios and some of your different electronics. So how much current is drawn by a lamp that has a resistance of 100 ohms when a voltage of 50 volts is impressed across it? So again, we have to be thinking that I equals V divided by R. And so this is going to be 50 divided by 100, which means we should see half an amp of charge flowing through it. Half an amp of current, my apologies. So what does Ohm's law tell us? Again, it just tells us that current is related to voltage directly and resistance inversely. Now, Ohm's law plays a big role in electric shock of human beings. The most dangerous part of being shocked is not the voltage. It's not the resistance. It is how much current begins to pass through you. Higher currents create more damage. And so if you get a very low amount, you might get a tingling sensation that borders on, whoa, I don't like that, to maybe even creates a little bit of pain, to where if enough passes through you, it will flow through your heart, cause problems with the circuitry that connects your brain to your heart and cause your heart to stop beating. And as you probably all know, a heart that stops beating is not a good situation. So for Ohm's law, what we again have to look at is, not just the voltage. Voltage, a 5,000 volt thing is more dangerous than a 12 volt thing. You're not too worried about your car battery, but 5,000 volts can definitely do some damage. But where it really depends is if you have a big enough resistor, it really doesn't matter what the voltage is. It's the current that we have to worry about. So your body varies in its resistance. If you are very dry, not sweating, maybe just took a shower, so you're very clean and you haven't perspired or anything after, you might have a very high resistance. If maybe 500,000 ohms. If you are standing in the ocean or taking a bath after a long, hot, sweaty day, you might have just 100 ohms in your resistance. So if you touch the electrodes of a battery with dry fingers and you're relatively clean, you have a high resistance, you're not going to get much of a shock. But if you are hot and sweaty working on your car and you touch across your battery, then you might get a pretty unpleasant jolt. Probably won't kill you, but it would definitely, make you feel uncomfortable. And so this is just a quick sort of rundown. Where do we see problems? Where do we not really worry about it a whole lot? So at 0.001 amps of current, you can feel it, but you're not going to, probably do much more than go, ooh, I don't want to do that again. You start getting about 5 times that at 0.005 and it hurts. It is very, very uncomfortable. 0.01, just double that 0.005, your muscles involuntarily contract. They spasm out. And I remember working in Chico when I was in high school. We were tearing apart a building while we were pulling out all the old lights so we could use them again. Well, in pulling these old lights out, from one of the circuits didn't get turned off, and I got a hold of some live wires, and literally my arms locked on the wires. And it wasn't until I dropped to my knees, I was working above my head, that I dropped to my knees and pulled myself off of the wires that I was able to finally get, control back of my hand muscles. But you get up and, further than that, and, you get 0.07 amps, and you can, it can be fatal. So that's not a very large current passing through you. So many people are killed every year by what I would refer to as being stupid, just by dealing with their simple 120 volt electric circuits at home. If you touch a faulty 120 volt light fixture or something like that, if you're dry, if you are, have a high resistance, it's not a big issue. But if you take that 120 volts and you've been sweating, or you just got out of the shower and you touch that faulty system, you can exert a pretty good pressure across yourself, which is going to cause a decent current to flow. And then there's going to be some problems. Now, if you're in shoes, usually your shoes provide a very good resistance, usually not a problem. Where we do see issues, you're walking around barefoot. It's hot in the summer, you just got out of the shower, things like that. That's where you can do some pretty good damage to yourself. So again, standing barefoot in a wet bathtub, not a good place to bring your radio. You accidentally drop the radio into the shower and you're getting lit up like a Christmas tree. Now, overall resistance is real low. So you're going to get a big current passing through you. That's going to be bad. Even drops of water collecting on the on-off switches of some devices can cause problems. This is why in your bathroom, if your house is relatively new, they all have those GFI switches in the bathroom to instantly cut off the power. So if there is some water that accidentally got in your hairdryer stuff, you turn it on, it's not going to shock you. It's going to turn the system off in your house, and you have to reset it and things like that. Now, distilled water is a very good insulator. It's not going to pass electricity through it very much, but our water that comes to our houses is not distilled water. It's got all kinds of ions in it that does allow electricity to pass through it much better. Again, it's not a great conductor, but it's enough to where there can be a low enough resistance that it can give you a pretty good jolt because of the little salt layer on your skin after you've been sweating and things like that. And that's going to drop your resistance down, to a couple hundred ohms. Divided by, divided into, 120 volts is going to give you a reasonable shock that is not going to be pleasant. So again, don't take your hair dryer into the shower to try and save some time. Leave that radio, on the bathroom counter. Don't bring it near the tub, because if it gets knocked in on accident, your dog comes in and wags his tail and knocks that into the bath with you, and you're not going to be a happy camper. So watch out for hair dryers. You can get shocked pretty good. So high voltage wires, why can birds sit on a high voltage wire? Well, it has to deal with the fact that if you're touching just one wire, or maybe you're touching two wires that are the same potential difference, there's no difference in potential between them. And so with no potential difference, there's no problem. Where these birds run into problems is on some of these high voltage power lines. They will touch the wire and then they touch the power pole. That happens and you got bird fricassee. He's fried, he's done, because now the pole is at a different potential than the wire, and current is definitely going to flow at that point. So, some of the action films, you see a guy, he falls from a bridge, he thinks, oh, I can save myself by catching this wire. Well, that is perfectly fine. Catch that wire, hold on to that wire, just don't touch anything else. Hope that the fire department comes to your rescue with a bucket or something like that, but do not let them touch you while you are touching that high voltage power line. You have to drop into the fireman's bucket, or you are going to shock yourself and the fireman trying to save you, because once that potential difference of the truck and the wire that you're holding on to get together, it's not going to be pleasant. There's going to be a flow of charge at that point. So ground wires. Why do we have a ground wire on our a lot of our devices? And again, a ground wire is one that's got the three prongs, the two that carry the electricity, but then this extra one here. That extra one is to bring any built up electricity back out of the appliance. Sometimes there's just a leakage of electricity in your washing machine, whatever it happens to be. And if that leakage is not removed by this ground wire prong, basically what's going to happen is you're going to touch the washing machine and then get a pretty good jolt. So this ground wire just runs back to the earth, essentially somewhere around your house, tied into your main panel. There is a ground wire that is pounded into the ground, and it just draws those build-up electrons to the ground, and the earth can handle them. You can't in a large quantity. So health effects, when you receive an electric shock, very typically there's going to be an overheating tissue situation where you're going to get a burn. It may disrupt normal nerve function. Again, that's going to cause your muscles to lock up, including your heart. And if that heart gets locked up, you go into cardiac arrest, and breathing and your heart can be jeopardized. Your heart pounding can be jeopardized. So if the resistance of your body was 100,000 ohms, what would the current in your body be if you touched the terminals of a 12-volt battery? So you're going to take 12 divided by 100,000, and it's not much. Okay, that was way below our 0.001, which we felt, but what was pretty much harmless. But what if you were hot and sweaty, your skin was moist, you'd been sweating, and maybe your resistance drops down to about 1,000 ohms, and then you touch a 24-volt battery? How much current would you draw then? Well, you're going to take 24, divide it by 1,000, and you get 0.024 amps. This is a very, very dangerous amount of current and could potentially do you some gnarly harm. So What causes the damaging effects of electric shock? Again, it's not the voltage so much or the resistance, it's the current. How much current begins passing through your body. So from there, we're going to skip 34, 7, 8, 9, and 10 and go to electric power. 7, 8, 9, and 10 have to deal with alternating current. It's not really tested by the state. It's interesting if you want to know what's happening with the electricity in your home and stuff like that. It's not important to our class, but some of you may find it more interesting than others. But electric power is equal to the product of current and voltage. So power, P, is equal to I current times V voltage. P equals I times V. And so what I encourage you to think about here is that any rearrangement of Ohm's law could be used to plug in for the I or the V here. And so power can have several different ways that we can find it depending on what we're given for the problem. So I might challenge you to go through and figure out what power equals in terms of current and resistance. What does power equal in terms of voltage and resistance? And so if you can do that, you're going to be okay. I, again, am going to throw this out in a video coming up sometime in the near future. So unless we have a superconductor, what we're going to see is that anytime a charge is moving in a circuit, it expends energy. And so this may result in heating a circuit. It could turn a motor. And so we have what is known as electric power, which is the rate at which electrical energy is converted into some other form of energy like mechanical, heat, or light energy. And so electric power is equal to the product of current and voltage. And so P equals I times V, or electric power equals current times voltage. If we look at the units, the mouse walks us through it. A watt is equal to 1 joule per 1 coulomb. Again, 1 coulomb per 1 second is a volt. The coulombs cancel. We're left with a joule per second, which if we look back, I believe it was chapter 9, way on back there in November or so, a joule per second was our power, which was a watt. And so if you look at your ordinary light bulbs, what you'll see typically is 60 watt, 120 volt. That's the rating that is on your bulb. And so the power and voltage would just tell us that the current that would pass through that, if we rearranged power equals I times V into I equals P divided by V, then we take that 60 watts divided by 120 volts, and we would be passing half an amp of current through that particular bulb. And so these ratings, again, tell us how safely we can operate our particular device on a particular circuit. You don't want to put 7 little space heaters onto the same plug. You do that, you're going to blow your circuit in your house. That's something that we will look at in the next chapter. Now, one of the things that is really kind of gaining traction is that this old lighting with these conventional wire inside light bulbs that we see, the light bulb goes off in your head, that kind of light bulb, is LEDs. And LEDs, gosh, you used to spend like $30 on an LED light bulb 10, 12 years ago. They're down to where they're pretty reasonable, like they're only $4 or $5 now. And they really last a long time. So they're much more efficient time-wise. And so even though these old bulbs cost maybe $1, well, if you're lasting 5 times as long and using 5 times less energy to run them, then you're actually making money in the long run. Even though they cost a little bit more to begin with, they last longer and use less energy, so it's more cost effective. So kilowatt is 1,000 watts. What we look at when we purchase our electricity from a power company is the kilowatt hour, and a kilowatt hour is a form of power. And so this kilowatt hour is, I pay, I think, something like 15.7 cents a kilowatt hour at Reading Electric Utility. I know that PG&E has kind of a tiered rating, and so if you overuse your electricity, you pay a lot more when you've used X amount than when you first start. And so unfortunately, that makes PG&E kind of a person, an entity that a lot of people don't like, because we end up giving them a lot of our money. So how much power is used by a calculator that operates on 8 volts and 0.1 ampere? And if we use it for an hour, how much energy is it going to use? And so we take the volts, times it by the amps. And so that's going to be 0.8 watts, and 0.8 watts over 1 hour, you would use 0.8 watt hours. And so that's not very much in terms of a kilowatt hour. And so it's not going to cost you a whole lot. Will a 120 watt hairdryer operate on a 120 volt line if the current is limited to 15 amperes by a safety fuse? So here you would want to take your power divided by voltage, which would be 1200 divided by 120. That would give you a current of 10 volts, and 10 amps is fine on a 15 amp fuse. But if you wanted to dry your hair faster and plug in 2 of these hair dryers at the same time, now you're running 10 for the first one, 10 for the second one, and you've got 20 amps flowing through this circuit. That's not going to work. It's going to blow that 15 amp fuse. So how do we express electric power in terms of current and voltage? It is that power equals current times voltage. Well, that finishes our notes for 34. Please pause and things like that as you need to. I know I'm kind of going fast, but I want to make these videos as short as possible so they don't drag out too long.